Hello everyone, and welcome back to another video provided by SVSU's online tutoring. My name is Joel, and today we'll be finishing up with section 8.5, applications of quadratic functions. And this video will be on a work rate problem and then a rocket example. So with the work rate problem, I have it outlined right over here, is that we have a company or an office that contains two copy machines. And machine B is known to take 15 minutes longer than machine A to copy the company's monthly report. But using both machines together takes 9 minutes to reproduce the report. And so we want to know how long it takes each machine alone to reproduce a report. And so there are two ways we can think about this. We can think about it as being the work done by machine A plus the work done by machine B, which is equal to the one completed job. But if we wanted to turn that into a quadratic equation, we have to instead use this bottom expression in order to solve for it. So we need to know what the rate for machine A is, and we have to multiply that for the time it takes both of them to do it, plus the rate for B times the time for both, equal to 1, which will be when the job is completed. So the rate for 1, well, we don't know what that is, so we just say that it's 1 over t, okay? And then for B, we also don't know what that is, but we know that it's 15 minutes longer than A, so it's 1 over t plus 15. And the time for both, is just equal to 9 minutes. So using these 3 bits of information here, we can substitute those in, and then we can set up our quadratic equation to solve for t. So we have the rate of A times 9 plus the rate of B times 9 equal to 1. And what we want to do here is that we want to get rid of our denominators here, and so to do that we have to cross multiply. So we have to multiply everything in this expression by t times t plus 15, okay? And when we do that, we end up with 9 times t plus 15 plus 9 times t equal to t times t plus 15. And then we distribute our 9, actually we just distribute everything to begin to simplify it. So we have 9t plus 135 plus 9t equal to t squared plus 15t. And then we combine like terms, so we have 18t plus 135 equal to t squared plus 15t. And then what I'm going to do is that I'm going to use the complete the square method, because I already know that this won't be factorable. So what I'm going to do is subtract 18 on both sides. So I'll have 135 is equal to t squared plus 15t minus 18t. And those two combine to give us negative 3t. And if we remember with complete the square, we take half of our b term and add it to both sides. So we have plus 1.5 and plus 1.5. So that gives us 136.5 equal to t squared minus 3t plus 1.5. And so this will factor into, so we have 136.5, which is equal to t minus 1.5 squared. And then we just take the square root of both sides, and we see that t minus 1.5 is equal to plus or minus the square root of 136.5. Add the 1.5 to both sides, and we have t is equal to 1.5 plus or minus the square root of 136.5. And so the solutions for t is that t can be equal to 1.5 plus square root of 136.5, or it can be equal to 1.5 minus the square root of 136.5. And so if you evaluate both of these in your calculator, you'll see that this second value gives us a negative number. So we reject this solution, and so the only one that we're left with is the positive value for the time. And this time is actually equal to, it's approximately 13 minutes. So then we say that the time for A to complete a job is 13 minutes. But for B, because it's T plus 15, we have 13 plus 15, which is 28 minutes. Okay, so that does it for the work rate problem. And then if we just scroll down here to get more room for the rocket, say that we launch some rocket, okay, so just like this, very nice parabola there, and then I'm going to draw my crudely drawn rocket here. Got some fire. And its model is given by h, which is equal to negative 25t squared plus 225t, where t must be greater than 0. And so what we want to know is that we want to know how much time wow, spelling, how much, not mush, how much time it takes the rocket to reach 350 feet. We also want to know how long it takes the rocket to hit the ground, how long till the rocket hits the ground, and then C, what's its max height. So to go about solving all that, if we, I'm going to erase all this now. So to solve for A, since we want to know how much time it takes to reach 350 feet, we plug in 350 for H, and so we have 350 equal to negative 25t squared plus 225t. And then we can subtract the 350, so we have 0 is equal to negative 25t plus 225t minus 350. And then we can divide everything by negative 25, since everything's divisible by that, just to make our equation simpler. So we have t squared minus, oh, let's see, I think that's 9t, and then what did I write? Positive 14. And this is actually factorable, and the factors that we end up with are, so 0 is equal to t minus 7, t minus 2. And so we see that t is equal to 7 and t is equal to 2. And so those are the two heights, or the two times rather, where the rocket is at 350 feet. So something like that. So if I give myself more room again by just getting rid of this. So if we want to now find out find how long it takes the rocket to hit the ground, all we have to do now is find out what our height is. So if the rocket is hitting the ground, that means that our height is at 0. So we have 0 equal to negative 25t squared plus 225t. And again, we can divide everything by negative 25. So we get 0 equal to t squared minus 9t. And what I'm going to do now is just factor a t out. So we'll have t times t minus 9. And then we set each of these equal to 0. So we have t equal to 0 and t minus 9 equal to 0. And solve for t here. So we have t equal to 9. And so we find that the rocket hits the ground at 0 seconds and 9 seconds. And the 0 seconds just means that it hasn't actually launched yet. It's actually still on the ground over here on the left side. But at 9 seconds, it's actually gone through its entire trip and landed back on the ground. Okay, and so the last bit there for finding the max height. So we have to remember that since we're dealing with a rocket, you know, it may be obvious that that the max occurs at the top here, but and that you know that the parabola opens down. But you can also take a look at your A term here, and so if that's negative, right, you have to also remember that you will know that a parabola opens downward. So if you didn't have this picture here, you'd have to mathematically remember what the significance of having a negative A value means. So since that's the case, we know that another way to say max height is to say the vertex, and so we can just use that relationship. So we have t being equal to negative b divided by 2a, and our b value is 225, and so we just plug that in, and so it's negative 225 divided by 2 times negative 25. So we have negative 225 divided by negative 50, and that time ends up being 4.5 seconds. And so that's the time it takes to reach our max height, but then we have to actually find out what that is. So we just take that max height and plug it into our equation. So we have h is equal to negative 25 times 4.5 squared plus 225 times 4.5. And so when we do that, we end up with, I have to plug it into my calculator right here real quick. We end up with 506.25 feet. Okay, that does it for section 8.5, applications of quadratic equations. There's a lot in this section, no doubt about it, but hopefully going through this series of videos will help you understand how to set it up and what you're actually looking for the problems, because that's really what this section's all about. It's about conceptualizing quadratic equations. Okay, see you next time.